So this is an example of solving a homogeneous equation when we have complex roots to our differential equations, auxiliary equation. So in general, just remember, so here's our original differential equation, a double prime plus by prime plus cy equals 0. Then we get that auxiliary equation, and there are three cases. Then in case 1, there are two solutions where m1 is not equal to m2. And in this case, then we get that the general has the form y equals constant 1 times e to the m1x plus constant 2 times e to the m2x. Make that a little smaller. Then the second case is when we get one repeated root. So this is when the only root of the equation is some number m, because the am squared plus bm plus c is really a perfect square. And in that case, the general solution would have the form y equals constant times e to the mx plus constant times x e to the mx. And we said this generalized, so if we had a higher order equation, we might have to multiply by more powers of x to the k. The third case is the case we're in, which is say that m is of the form alpha plus or minus beta I. So here alpha and beta are real numbers. The alpha is always called the real part, and the beta is called the imaginary part. In this case, then the general solution always has this form. General solution will be of the form y equals e to the alpha x, the real part, times constant times cosine of beta plus constant times sine of beta x. And this came from Euler's formula, that when we write e to the I times theta, what that means is cosine of theta plus I times sine of theta. And we looked at why that was the case using Taylor series as a proof, being able to expand e to the I theta using a Taylor series expansion for e to the x and determine that the odd powered terms all had i's on them, and ended up building what looked like the Taylor series for sine and the theta, and then the with an I in front of them, and the even power terms ended up building a power series that looked like a power series for cosine of theta. So that was how we determined that formula was true. Let's look at an example. And I'll remind you again how we went from having something that should still have i's in it to something that doesn't. So let's look at the following example. It's actually going to be an initial value problem. Y double prime minus 2y prime plus 5y equals 0. And let's solve the IVP, where y of 0 is 2, and y prime of 0 is negative 1. So our first step is always to get the auxiliary equation. So m squared minus 2m plus 5 equals 0. Then we find the roots via the quadratic formula. So m should be equal to negative b plus or minus the square root of b squared minus 4 times a times c, all divided by 2a. So in this case, simplifying that, we get 2 plus or minus the square root of 4 minus 20 all over 2, or 2 plus or minus, that's the square root of negative 16, so that's 4i all over 2, or 2 plus or minus 2i. So the real part of that solution is 2. So since the real part is 2, this tells me that my general solution will have a e to the 2x part in it. And then because the imaginary part also happens to have a coefficient of 2, that tells me that the argument of the sine and cosine portions will also be 2x's. So these 2's are from the imaginary part. So now to solve the initial value problem, I'm going to compute y of 0, which would be e to the 0 times c1 cosine 0 plus c2 sine 0. So that ends up just being 1 times c1. And therefore, we get that c1 must be, going to our initial value information, we wanted y of 0 to be 2. So that tells me that c1 is 2. So let's go ahead and find the other value. I found that c1 was 2, and so replacing that in the equation, I have the 2 here. So to find the second coefficient, I'm going to need to find the derivative. I'm going to use the product rule. So the derivative of e to the 2x is 2e to the 2x. And that'll be multiplied by 2 cos 2x plus my c2 sine of 2x. And then the other term will be the first function left alone times the second function. So derivative of the second function will be negative 4 sine of 2x plus 2 c2 cosine of 2x. So now let's go ahead and compute y prime of 0. So we're going to get 2 times e to the 0 times 2 cosine of 0, so 2, plus c2 times 0, that would just be 0. Or sine of 0, that would just be 0. The second term will have an e to the 0 times negative 4 sine of 2 times 0, so that's just 0, plus 2 c2 cosine of 0, which is 1, so there we go. So what we're left with here is 2 times 2 plus 2c2. And if we go back and look at our original initial condition, we wanted that initial condition to be y prime of 0 equals negative 1. So I'm going to set that equal to negative 1. I'm going to subtract 4 from both sides, and I get that c2 is negative 5/2. So y of x will be e to the 2x times 2 cosine of x of 2x minus 5/2 sine of 2x. And it's always a good idea to triple check that your solution works.